Hello everyone, my name is Sebastian Diaz, but everyone calls me Sebo. Today I'm going to be presenting some work I did with the Magnetic Resonance Imaging Group here at MIT. My project is titled Design of Novel RF Pulses for Fetal MRI using ring factorization to reduce heating and improve imaging speed. Before I begin, I want to give a special thanks to the MSRP program for providing financial support, as well as Borja and Gagowski for providing the parameters for which I compared my results to. Before I get into my findings and the implications of those findings, I want to give a brief overview of the physics of MRI. So in MRI, we are targeting hydrogen nuclei, and when we expose these nuclei to a static magnetic field, they begin to process at something called the Larmor frequency. And if we match this Larmor frequency with an RF pulse, we can actually flip the magnetization vector of that hydrogen to any degree we want. And this can be seen in the bottom left and bottom right. And in this case, we are flipping it 90 degrees. So the broad implications of my project is in regards to fetal imaging. And fetal imaging is particularly difficult for three main reasons. Number one is the motion and unpredictable motion of the fetus. Number two is the time in regards to getting a quality image before the fetus moves, as well as for the patient comfort and getting them in and out of the scanner within a set amount of time. And number three is the safety issues that result from this time constraint. And because of this time constraint, we are applying a lot of RF pulses, which result in the heating of the tissue, in which we denote by SAR, which is signal absorption rate. In regards to the RF pulses I talked about before, they have two components. One is the excitation pulse, which flips the magnetization vector 90 degrees. And number two is the refocusing pulses, which flips the magnetization vectors 180 degrees. And this is particularly useful because it realigns the magnetization vectors all with each other, so we get a spin echo, which result in the maximum amount of signal that we can get. And this can be seen in this typical spin echo sequence, a fast spin echo sequence, and then when we turn up, it's even faster for fetal imaging, which through HASTE, which is a Siemens trademark sequence. And that you can imagine that this deposits a significant amount of energy within the patient. So when we're looking at RF pulse design, we're really entertaining and trying to find a good balance between SAR and localization of a signal. And when we have a higher time bandwidth product, which is basically zero crossings in the RF pulse, we will have great localization, but high SAR. And when we have a lower time bandwidth product, we will have poor localization and low SAR. So my project is trying to find the best of both worlds in regards to this. And the way we do this is through novel algorithms that I'll talk about within the next slide. So when we're looking at pulse design and their algorithms, we are looking at the Bloch equations and the flip angle nonlinearity. And this nonlinearity makes the design of pulses very difficult, as we can't jointly solve for some parameters. And this is seen in the Schneider-Lower algorithm, which came out in the early 90s and late 80s, and it required describing spins through these two complex polynomials denoted by the Cayley-Klein polynomials. And these polynomials are bilinearly coupled, which means that we only can solve for these sequentially, at the time at least. And this is where my project is based upon the application of a new method where we actually jointly solve for these. So this jointly solving that I was talking about is introduced through SLfRANK, which was a paper published by Frank Ong in March of 2021. And this jointly solved the parameters through convex optimization and ring factorization, and results in more optimal pulses with more linear phase and less pulse energy. So now for my results. My results are two pulses, an excitation and refocusing pulse. So for the excitation pulse, I had a time bandwidth product of 2.75, a gradient strength of 0.095 Tesla per meter, and a pulse reduction of 9.75%. As you can see, the phase is more linear, and we replicate the slice parameters. As for the refocusing pulse, we get a time bandwidth product of 2.08, gradient strength of 0.058 Tesla per meter, and a pulse energy reduction of 22.55%, which is very significant because, as I was explaining with the pulse trains, the 180 degree pulse gets played a lot more times than the 90 degree pulse. And as you can see, we replicate those parameters. So in regards to conclusions and future directions, my pulses provide a more linear phase while also reducing energy and replicating the parameters that are currently used in the clinic. So now we are going to confirm what I calculated through phantoms, hopefully eventually transitioning into the clinic, which will be used to reduce the acquisition time. And also, this proves that we can actually probably use this methodology in other sequences, in other SAR-limited sequences specifically, which is very exciting. Thank you.